So this is the, the presentation about coupling multiphysics in environmental problems. And first, I would like to, sorry, because it's the last slide, that is also the first one. I would like to thank Angel and Rina for inviting me and for letting me share this seminar with so excellent researchers that are coming next, are coming after me. So I want also to thank to the computational mechanics group of the Polytechnic University of Madrid, and in particular the researchers of the computational geomechanics line. The researchers and professors and also the PhD students, former and the current students. And some of the results that I'm going to present today also comes from a collaboration with the University College London, with Susana López Querol and our student Mian Xie. This is the outline of my presentation. First, I want to talk about the basic science, because I want to present all the lines or the basic science that we make research, mesh-free methods, multiphysics formulations, and non-local failure. And then I want to present or introduce in several slides the two main lines of the current project that we have about landslides and CO2 storage. About mesh-free, they were born to deal with several problems with the distortion of the mesh. If we focus on the Lagrangian approach, we can see how the mesh follows the displacement of the movement of the body, but in the Eulerian approach, the mesh is not moving, but it is only moving the particles or the material. It has some advantages and disadvantages in depending on what we are seeking. For me, the main ones are in large deformation. Lagrangian methods are difficult to handle because we can see a very distorted mesh that leads to numerical error. On the other hand, with Eulerian methods, it is difficult to track the mass, the energy, and the state of the material. So the mesh-free methodologies arise in order to solve these issues. We can see that the mesh-free methods do not require connection between nodes because the interaction between nodes or particles is made through a neighborhood. So the mass or kinetic energy is not dependent on the element. We don't have elements anymore. We extrapolate these properties to the nodes or the particles. And this absence of the mesh allows Lagrangian simulations to deal with this distortion of the mesh easily. So if we make a classification of the numerical methods between Eulerian or Lagrangian, the traditional finite volumes or finite difference or finite element, and for the mesh-free methodologies, we have in the Eulerian frame the MPM, the material point method, which is not a purely Eulerian frame, but it is based on a Eulerian background mesh. And in the Lagrangian frame, we have SPH, the smooth particle hydrodynamics, that is maybe the famous one of these mesh-free methodologies. There are many of them. It is true that not all of them have a long career, because not all of them are we are working with them. But it is true that there are several of them that I think they came to stay in the numerical community. Some of them are the ones that we know because we have published several publications and we made research on those fields. We have first the SPH, which is the first one. It comes from the 70s of the last century, and we can find that as I said, the element or the mesh is not in our formulation, but we change for a neighborhood which is defined by a weighting or kernel function. It is not any function. It must satisfy several properties like being differentiable, decreasing, and compactly supported. And obviously, not any function with these properties is able to reproduce the SPH. And we can see in this slide how different types of kernels produce the different types of instabilities or numerical errors. So the choice of this kernel function is essential to get accurate results. We can see here a simulation of a channel of water with SPH. It is not from our group, it is from dual physics community, which is a group from the University of Vigo. And they have this open source code for SPH. So we can see how this distorted, this large deformation is allowed in SPH. Of course, as it is the first mesh-free methodology, it has lots of deficiencies compared to the rest of the mesh-free methodologies. For me, the most important ones are the prescribing the boundary conditions, because it needs to have a compact area of support, and the tensile instabilities, because this methodology is not based on the traditional Galerkin approach, so it doesn't have the total integration support that it needs a computational technique. So about the boundary condition, also for the tensile instabilities, some technologies appear, but in my opinion, they are kind of artifices to overcome this situation. So they work, but what is behind is not, let's say, too numerical or too accurate. About the PFEM, the particle finite element method, it is very simple because what is behind is a finite element calculation, but step by step, all the connectivity is deleted, and we take a cloud of particles or node. Then we construct again a mesh in order to make the calculation, but this mesh must satisfy the Delaunay triangulation properties. So it is difficult to find with this methodology a distortion of the mesh that doesn't allow us to get accurate results. So it is very powerful and strong, and here we can see the work of one of our students, a master student, with you can see here how some elements are deleted from the calculation, and some triangles appear here in the part of the material is moving. The set of the mesh-free method that we have been working with is the OTM, the optimal transportation mesh-free. It is powerful because it is based on a Galerkin discretization with nodes and material points acting as an integration point, the traditional integration point of the finite element method. Also, it is easy to handle with the boundary conditions because we have the same properties as in the finite element in the boundary node. So it is a very strong methodology. As I said, we can start from a traditional finite element discretization of material points and nodes, and we can delete this connectivity and create another one which is based on the distance between nodes and material points. The safe function that is governing this mesh-free method is the local maximum entropy, which is very feasible because depending on just one parameter, this parameter gamma, it is able to make or very large or very close neighborhoods and safe function support. In the case that we want to localize any problem, we can use this gamma very high, and if we want to smooth out our results, we can use gamma, a low value of gamma, and even we can mix both high and low values of gamma in the same body and the same calculation. Some results of this is the original one, the ones that proposed Professor Bolli, who worked with us in several research. And this is the impact of a bullet in a plate, and you can see also the impact of this bullet with different degrees, different angles of impact. And the last, but not the least, that this mesh-free method that I'm going to talk is the MPM, the material point method. It is the last because it is the one that we are working with in the last years, because it is strong, it is robust. It is also based on Galerkin approach, because we have nodes and material points. The methodology is the material points carry the information of the material, and they move along a fixed background mesh. So the calculation of the safe function is made with the position of the material points in the mesh. All the information is transferred to the nodes, and then again, when the material point is moving, it's transferred again to the material points. So it is the main advantages is that it is cheap. It can employ the isoparametric traditional formulation. But of course, when we cross a cell between one element with previous elements that are now our cells, from one cell to other cell, we can see grid crossing errors. So it is due to the different location from this point to this point in between two steps. So the main advantages of the new MPN methodologies are seeking the solving this grid crossing error. Okay, the last two ones, the B-spline MPN and the local maximum entropy, the previous function that I showed, MPN are those that we have been working with in the last years, and we have to say that they are very strong because as the neighborhood is it is able to cover several cells, we don't see this transfer between one cell to the other cell. Some results, this is a results of fluid impacting against a wall. And this is the difference between the traditional MPM and the local maximum MPM, which is this second one is smoother, and it is able to reproduce smooth solutions of the formation of a localization of the shear band. I want to also to show you two videos. They come from the computational graphics community, and the point of this is that they employ MPM with a kind of physical positive model somehow to reproduce the snow of the film frozen. And in this one, we can see the deformation of a bread. So they employ this in films, in Disney films, in order to reproduce very, very large deformations of the material. So the following topic that we are working with is the multiphysics formulation. In the last year, because of the project that we are working, we are seeking what in soil we say the whole formulation, is the THMC formulation, thermohydrochemomechanical formulation. It is true that the chemical part can be considered uncoupled from the rest of the formulation. Of course, we have to include, but it is not so simple at the very beginning. So we have to study first separately this chemical part. The other three, the mechanical, we are studying soft and quasi-brittle materials. We are also studying fluid and gas materials in the hydraulic part. And finally, the thermal part is led by external heat or the heat generated by the change of the phase of the material. So if we focus in the THM formulation, it is led by the conservation of mass equation given by Lewis and Scheffler. So it is true that the scale of the temperature is different, very different from the scale of the soil and the water. A consolidation process is about days, and a change of 1 degree of temperature in the soil is about months or years. So we can also uncouple at least the variation of the temperature along the time. So in soils, if they are not compressed somehow, we can also avoid the gas pressure, the air pressure, and we can consider that the external heat is also equal to 0. So the equation of an unsaturated soil is this one. So the important things are the compressibility of the water, the compressibility of the soil, the degree of saturation, and the variation. This CS is the specific moisture content. That is it's a measurement of the variation of the degree of saturation depending on the pressure. Also, the compressibility of the solid is much bigger than the compressibility of the water. So this term, in general, can be avoided from our calculation. So the way to calculate this is this equation, the equation of the conservation of mass, together with the momentum balance equation, the equation of the mixture and the fluid, and we can solve them monolithically in order to calculate the variation of solid, water phase, water displacement, and pore pressure. We can, of course, it is very nonlinear, it is expensive, it's a very expensive calculation. We have to, as we have so many nonlinearities, we have to make a very, very small time step in order to capture the variation of any property. So we can, with a UW formulation, so the goal of this formulation is to delete 1 degree of freedom of the problem. In this case, the pore pressure. If we integrate the conservation law, of course, in order to get the pore pressure, a pore pressure that can be included in the 2 first equations, we can find that there are some terms that are actually velocities of something, of the pore pressure, of the solid, or the fluid. But also we have 2 terms that we don't know how they vary along the time. So it is not a very simple integration. We have to analyze this integration numerically or analytically in order to reach this UW formulation that is cheaper than the UWP formulation. From the UWP formulation, we made this problem of infiltration. We have a dry soil, and we see how rain, for instance, we can get the infiltration along this column of soil. The difference between this example that I show from this paper and the one that we obtained is that we add to our formulation all the inertial terms. So we have these differences here that comes from the inertial, from the velocity of the infiltration. So the main trend is the same, but we have these variations because of this. So we have to analyze, and we did for the saturated equation with degree of saturation equal to 1, we have to analyze how is this influence of the inertial terms. These are the equations with saturation equal to 1. And normally, if we don't have vorticity, that is not normal in a soil or in a rock, at least not in a rock mass, a fractal rock mass, so we can delete the second order terms of our calculation. So we can solve the problem with complete formulation, as I said, UWP or UW, or the UP, that this one neglects some inertial terms. And it comes from the 80s, the research of Tienkiewicz and et al. And they see that there are, depending on the frequency of the load and the permeability of the material, we can, in the zone 2 or 1, employ reduced formulation, or if we are in the zone 3, which is a very high permeability and very high frequency of the load, we should employ the full Biot equations. So here you can see a problem of a dynamic load, a vibratory load along a saturated column, and we can see the differences between the complete and reduced formulation. So it is important to take into account that the complete formulation is essential if we want to deal with a very high frequency of the load. Of course, not only for saturated soils, but also for unsaturated soils and for any thermohydromechanical problem. One nice simulations where they come from my thesis. The first one is an earthquake acting in a soil with a dilatant material. So it is as it is dilatant, the material gets stiffer, but if we have a contracted soil, finally we can see how is the deformation because of the liquefaction of the soil. And of course, in these kind of problems with earthquake and these very high frequency vibratory loads, it is essential to work with full Biot equations. Finally, we have to talk about non-local failure models that are the last branch of our research. We started working with the approach of Pandolfi and Ortiz called A-generation approach, which is working quite well with brittle fracture and also with very high loading rates. It is based on the comparison of non-local energy of a material, which is calculated through a neighborhood also, compared to the critical energy of the material. So it is not working well for quasi-brittle fracture. So we change the equations and rearrange in order to calculate a non-local stress that we compare with the strength of the material, and then with a cohesive law we can create a cohesive zone in the material in the crack, varying from the stress equal to the strength of the material, and decreasing this strength until the critical opening of this fracture. This variation of the strength of the material is made through a damage variable, which is very similar to those phase field methodologies that we can see in the literature. So several results that we obtain with these two methodologies, Eigen erosion and Eigen softening. The first one is made with a 3-point bending test, in dynamic, and we can see the strain obtained in the different strain gauges is very close to the eigensoftening one, but the eigenerosion overestimate the strain and the stress of the specimen. We can see here two simulations, and we observe the sigma 11, the horizontal stress, and we can see how the first one, the eigenerosion approach, overestimates the stress inside the specimen. So we can say that the eigensoftening is working better for this kind of materials, quasi-brittle materials. We also test this methodology against a mixed mode fracture with fiber reinforced concrete with different quantities of fibers in the material. And of course, the crack pattern is very different from all of them. H00 is without fibers and with a low quantity of fibers and a very high quantity of fibers. And we can see that the crack is following very well the crack pattern that we find in the experiments. And finally, we extended this methodology to soft materials. In this case, we can find in the literature the behavior of thin soft layers, or mainly clay layers in the nature, and we can see how they suffer this degradation depending on the strain that they suffer. Actually, it's not this variation is not a plastic strain, it's any strain, any cycle or elastic or plastic will affect to the degradation of this material. So we try to test with this shear band of one thin layer, where first we trigger the plastic behavior of the material, and then with a cyclic load that can be similar to a set of rain cycles, we can see how the material strength degrades, and then finally they fail all these points of the shear band because of the degradation of the yield. We can see here that at the very beginning we have plasticity, but then there is no accumulation of the plastic strain, but the material is degrading, and then finally the whole structure will fail because of this degradation. And again, it is not local degradation; it is a non-local degradation of the material. So, in very okay, these 30 minutes, in more or less 5 minutes, I will explain the two lines that we are following in our research group. The first one is the landslide risk assessment. That is the topic of the two last projects of the group, which are mainly based on the SPH calculation or simulation of landslides. In this case, we are making 3D simulations with 2D meshes because of the depth integrated model. This is a model that we don't calculate the Z direction, but we integrate thanks to a finite difference mesh that is made in every point depending on the height. So we don't have the information of any point in the height, but we have the information of the whole mass integrated. With this methodology, we assess so many landslides. I will present two: the Frank landslide in Alberta, Canada, which is a rock avalanche. This is some pictures of that avalanche, and we can see here how the landslide propagates. What this one with the height of the avalanche. If we compare both, the not experimental result, the real results of the landslide and the numerical simulations, they fit very, very well. Also, we have a very different landslide because this is a soft soil, clay, that also happened because of the rainfall in that area in Hong Kong. We can see here some simulations also about this landslide, and here we can also see how the landslide impact against a road. And here we can see the simulation, and we can see how close it is to the reality. And finally, the second line that we are following is the NPM modeling of landslide, which is the name of the thesis of Mian Xie from UCL. And he's working with NPM with some improvements of the one that we have seen before. The first one is that he's solving some NPM instabilities with a B-spline NPM. He's also working with two different sets of material points, one for the fluid and one for the solid. That is essential when we have very large deformation because any material go in a different way. And we also are studying the triggering and propagation because in the previous examples, you only can see propagation but not triggering, because now in the literature it's difficult to find constitutive models able to reproduce both triggering and propagation. Okay, so here you can see the modeling of this experiment that is in the literature. It is not a soil, it is done with aluminum bars, but they can be calibrated with a more Coulomb traditional constitutive model. So with this model, we did some simulations, and we can see how close is our simulation to the real experiment. Okay, let me show again. It is very, very close. It is very smooth without any instability. So we are very proud of this result. Also, we have the second result that I told you, two sets of material, the soil and a column of water. And we can see that they are both different sets of materials, and how the water acts and breaks the slope of the soil. And finally, the last of our project is the DISCO2 store project, that is an European Union project, which is called Discontinuities in CO2 storage. The main purpose of this is to deal with the increasing of the CO2 concentration in the atmosphere, and it is part of not a project, but at least a methodology to capture, transport, and storage the CO2. In this case, the storage is proposed in a geological reservoir, in a abandoned reservoir of oil, with the abandoned wells and all the places where the oil was in the previous stage. The difficulties that we can find if we store the CO2 in this rock mass is that we can see migrations, maybe in the faults of the rock, in several fractures made with the injection. When we inject CO2, we can provoke fractures in the rock, or also in the cement that is close or not close around the wells. So for all these three ways, we can suffer migration of CO2. So this project and the partners that are here want to study how is a discontinuity in the rock mass and how is the behavior This project is classified into 7 work packages. UPM and my university, my group, is working on 3 of them. The first one is the work package 4, that is the mechanical characterization of discontinuities. It is both experimental and numerical. The experiments we can see are several laboratory tests of the discontinuity, some shear and triaxial tests against an intact or fractured rock in order to see how is the behavior of this interface. And the second stage is to include the CO2 injection in these experiments in order to see how is the variation with a dry specimen. And then we have to model this interface with a numerical simulation. In the literature, we have found a traditional more Coulomb problem. And of course, the friction is different because the friction depends on many parameters of the interface. But of course, this law and experiments are very close right now, so it is a very starting point to model this behavior. But when we will introduce this in a hull simulation with pore pressure of the CO2, we will find a very interesting issue that this interface behavior is only modeled as a mode 2, but maybe it is not true, because if we are creating a discontinuity and the pore pressure is getting inside, maybe it's opening somehow the crack. So maybe we will find also a mode 1 in this interface between rocks. The work package 6 is the chemical work package, because it is studying the behavior of the cement paste that is around the well of injection. So this cement paste is suffering several chemical reactions because of the interaction with the CO2. So these are we have in the group several publications with the software Bill, which is from the Col de Pont, one of the partners of the project. But we have to include these reactions in a whole software. This is the last of the work packages, the work package 7, that includes all the THMC interactions that we have seen in the previous work packages in a reservoir scale modeling. It is challenging because, as you can imagine, a reservoir is huge and the scale of the reservoir is huge, but the scale of a discontinuity is not so big. So it is difficult to model with the same scale an interface of material, of rocks, and also the whole scale of a reservoir. So this is the project, and these are the 2 following years of the project that are challenging, as you can imagine. And that's it. This is my presentation of these environmental problems that we are studying with these numerical tools.